Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, April 29, 2022. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a flowery spring evening in my hometown of Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I am grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry science and education associates, far-flung friends, family, and other curious folk. Thank you for participating. This evening, I will talk on surfing the Auroral Cascade, insights and enigmas. The associated research was done over the summer of 2021 with student Mu-Cheng Ma, who goes by Max. As you will see, we had some success explaining how the dominant colors of auroras are produced by collisionally excited oxygen atoms at altitudes of 100 to 200 kilometers. We had greater difficulty understanding how incoming electrons from the solar wind attain the velocities necessary for collisionally exciting those oxygen atoms in the auroral zone. So let's go to it. I will now share my screen and begin the presentation. So share the screen, share, and slideshow from the beginning. All right, so as I said, surfing the Auroral Cascade, insights and enigmas. Some of you may be familiar with the Snoopy characters. I've actually used them in the past. What's a small active speaker? There we go. And I've used them in the past to highlight what's going on in the Milky Way, but this is appropriate for the theme of auroras. And for you amateur astronomers, you might recognize some of these star patterns here. This is the belt of Orion and the sword of Orion here, and this is the Pleiades right here. So this is taken, I believe, in Iceland, this picture. So here we go. Auroras occur in both the northern and southern night skies. So for the north, they're called Aurora Borealis, and the south, they're called Aurora Australis. And they're usually at latitudes that are pretty high, exceeding 60 degrees north or south. But sometimes they attain more intermediate latitudes, like where I live in Cape Ann at around 40 degrees. And this is proof of that, a view from Lanes Cove in Gloucester, Massachusetts, showing aurora with different colors. The auroras, their incidence and intensity increase towards the poles. That's because Earth's magnetic fields converge there. That's an incredibly, what was this called? The vortex aurora. And this followed a coronal mass ejection from the sun, a solar storm. And this is what happened in the auroral zone. Pretty impressive. So basically, where the action is occurring is at these higher latitudes, both in the northern hemisphere and the southern hemisphere. So if you want to see auroras and you want some guarantee that you'll see them, you could go to Alaska, or what is this, Ellesmere Island, Greenland, Iceland, and Sweden and Norway. Those would be good. And a lot of Russia is within the what is known as the auroral oval. And in the southern hemisphere, the auroral oval is basically over parts of Antarctica. And you might notice that the oval is not centered on the spin axis, and that's because the magnetic axis, the axis of the magnetic field is not exactly coincident with the axis of spin. And if you're interested in learning about auroras, you can follow them on what is it? Aurora, what is it? spaceweatherlive.com or spaceweather.com, and you can even receive aurora alerts. I'd have to say that I haven't had much luck. I've only seen auroras a few times, back in the late 60s from my home here on Cape Ann, in the 80s from the Seattle area, and it was a light polluted area, so it must have been a very bright aurora then. And then also in the late 90s, I saw it from Massachusetts, from Boston to Cape Ann. So I haven't had that much good luck. A bucket list, as Eleanor said, to go someplace where you're guaranteed to see auroras. You have to go there at night, and of course that's a special time of year, so close to the poles. So it would have to be in the December period in the southern hemisphere, and in the December period in the northern hemisphere. You know, the months around December and the months around June for the southern hemisphere. You want to be there at night. So not only do auroras have interesting structures and colors, but they also move in real time in response to changing currents of charged particles along these magnetic field lines. And it's these currents of charged particles that move around as the magnetic fields do too. And let's see if I can show this video from the International Space Station. And here we go. Baffin Island, by the way, yes. So here's the space station. It's moving as well, but you can see that the aurora, the ripples are changing. There's stuff going on. This whole part of the atmosphere, this transitional part of the atmosphere from the molecular lower atmosphere to the ionized plasma upper atmosphere is very dynamic. Okay, so now we get rid of that and go back to the PowerPoint. And here we go. Okay. So you can get involved as well as a citizen scientist to help with aurora research. The Zooniverse has a whole lot of citizen science projects, the Zooniverse portal. And one of them is this Aurora Zoo, which several of my students in a citizen science course checked out, and it ended up being their favorite. And so this is typical of the Zooniverse projects. They tell you about it. You have a place to classify various phenomena based on what you see. You can interact with others, including scientists, in the talk function. So it's all there. It's a pretty neat way of getting involved, and you don't even have to. You don't even have to know much beforehand. So now I'm getting into the Zooniverse portal, and here is basically an example where they're showing a piece of an aurora, and they ask you some questions. So you might choose aurora everywhere, or you might choose edge. but definitely you would not choose no aurora, and probably not irregular blobs, and not coronal rays. And so this is the sort of classifying that you can do. They're just trying to figure out how these auroras move on a finer scale. Okay, so now I want to get out of this. All right. So to understand more, you have to dig deeper, and you have to really get a hold of what is causing the aurora in terms of these subatomic particles that are being emitted by the sun in the form of the solar wind, and sometimes in the form of great storms like those coronal mass ejections. And they impinge upon the Earth's magnetosphere, which is like a protective shell produced by the Earth's magnetic field. It compresses on the inside and then kind of stretches it out on the opposite side. And it ends up, particles get in, still penetrate the magnetosphere, and they get trapped, and they can get accelerated back down towards the Earth's atmosphere. And I have another video that helps you see that.
Our sun is constantly blasting huge amounts of hot plasma out into space. All those charged particles have a big effect on everything in their path. So what's protecting Earth from the solar wind and solar storms? Earth's thick atmosphere provides some defense, scattering and absorbing solar particles before they reach the surface. But our planet also has a secret weapon, a strong magnetic field that projects into space, mostly generated by molten iron alloys moving in Earth's outer core. The area of space where the magnetic field interacts with the solar wind is called Earth's magnetosphere. Its shape constantly changes as it's bombarded by solar particles. As positively charged protons and negatively charged electrons enter the magnetosphere, most of them are deflected around Earth, long before they reach the atmosphere. The magnetosphere really gets tested when big solar storms, carrying more plasma and traveling at higher speeds, are on a collision course with Earth. While most of the plasma is deflected, some of it gets trapped in the magnetosphere and funnels back toward Earth along field lines emanating from the poles. As charged particles from the sun collide with nitrogen and oxygen molecules in our atmosphere, they create the cosmic light shows known as auroras. The bigger the storm, the further from the poles auroras can be seen. Some storms are so big, they interfere with satellites, cause planes to alter their routes, and can create other problems. The vast majority of the time, these inconveniences are pretty minor, but the next time the solar version of a perfect storm overwhelms Earth's magnetic shield, we might not be so lucky.
Yes, these sorts of storms have been the cause of giant blackouts in, I think, in Northeast, including Quebec and much of the Northeast United States. Also, it leads to corrosion of the big pipelines that are in Alaska. So, and of course, they can disrupt satellites quite a bit before they get to hit the Earth's atmosphere. All right. So this is an atmospheric phenomenon. And let me give you some context. Where you and I live and breathe is in the troposphere. The y-axis, the vertical axis, is altitude. And you can see that most of us live below the top of Mount Everest. And here, the temperature goes down with altitude. And then in the stratosphere, where the jet planes exist and the high altitude balloons can go up to. The temperature backtracks to getting warmer with height. And this is also where the ozone layer, O3, oxygen 3, which protects us from ultraviolet light from the sun. But you have to go even above the stratosphere and even the mesosphere to get to the thermosphere, where the temperature is again rising with altitude. And this is where you're transitioning from, I should go from the bottom, from molecular to atomic, and then to ionized plasma. And so this is a special transition zone where you can have both atoms of oxygen and molecules of nitrogen. And even beyond that, you have the magnetosphere, which deflects the particles towards the poles, and where they descend to lower altitudes, such as this thermosphere, impacting and exciting atoms in the thermosphere. The exciting area appears to be between 100 and 200 kilometers, which isn't shown here on this plot. All right. So Mu-Cheng Ma and I first asked a simple question. Why do most auroras appear green at the lower altitudes, shown here, and then red at the higher altitudes? The red is hard to see with the naked eye, but cameras pick it up rather well. And the first aurora that I saw, I distinctly remember red. So that's the question, a simple question. What makes the auroras have the colors that they do, the typical colors? So it didn't take long for us to learn that the auroras are produced by the spectral line emission from oxygen atoms in particular. And here I show the spectrum, the spectral line, the emission line spectrum of oxygen atoms. There's a green emission, and then there's two red emissions at very specific wavelengths. This is around 550 something nanometers. And this is at around 630 nanometers. In addition to these basic green and reds, there's additional colors of blue sometimes seen, and other reds seen due to nitrogen molecules. But we have focused mostly on the oxygen. The other thing to note is that when you go from 100 kilometers, where the green seems to be very prominent, to 200 kilometers, where the red is more prominent, there's a tremendous decrease in the density of particles. This horizontal axis is the particle density. So you go down from basically 1 trillion particles per cubic centimeter to about 10 billion particles per cubic centimeter in this mesospheric area, this thermospheric area, this zone. And so that ends up being a critical change. And this gets into the actual quantum physics of the oxygen atom. And here is an energy level diagram of the oxygen's outermost electron. The electron usually stays in this, it chills basically. The electron stays in this lower energy level. But if it gets hit by an electron with sufficient velocity, it can go up to this level, all right? And it takes an energy, an electron energy equivalent to a velocity of about 1,000 kilometers per second to get it up here. And it will then go back down to its rest state by emitting light in the form of a photon. And it first emits light at 5577 angstroms, or 558 nanometers. And that's the green emission right here. And I think most of the emission is in the green. That gets it to this level. And from there, it will emit in the red wavelengths, the 630 nanometers or 6,300 angstrom levels. Okay, so those are the two transitions that lead to the green and the red emission respectively. But wait, there's more. It takes different amounts of time for this transition to occur. The green transition occurs relatively quickly, within a second, 0.83 seconds, whereas the red transition, the electron transition of energies leading to the red emission, that takes much longer, about 159 seconds. That's almost 3 minutes. This is because this is known as a metastable level in quantum physics. And the problem is that that is a lot of time, and the atom could be hit by an electron well before it emits, makes the transition and emits. And so the electron can be collisionally de-excited before making the jump. And so that's an issue with the red emission. And that issue becomes greater at higher densities, where you have more collisions. So the basic relationship has to do with the rate of collisions. That's P sub C. And it goes with the particle density n. It goes with how big your target is, the target area as well. You can get greater hits if your target is bigger. And it goes with the velocity. If you have a swarm of electrons, if they're going faster, you'll get more hits per second as well. So this is the basic equation. And you don't want the rate of collisions, the collision rate, to greatly exceed the transition probability of the electron. For the green transition, the transition probability is very high, but for the red transition, the transition probability is very low. And so if your collision rate is much greater than your transition probability, you're not gonna have the transition, because it'll get de-excited. That is why the red emission is squelched at the lower altitudes. Those altitudes have denser gas. With the denser gas going up, the collision rate goes up. And so we were able to sort of qualitatively explain why you don't see the red emission at the lower altitudes. But we could go further. We could examine the parameter space, and I'll guide you through this. This is a plotting routine called Desmos, and all the quantities. Here's the collision rate in the vertical axis, and it's a log has been taken. It's a log plot. The velocity is on the horizontal axis, and the log has been taken. For example, 2 corresponds to a velocity of 100, and 4 corresponds to a velocity of 10,000 kilometers per second. And that relationship, which I just showed, basically ends up being a linear relationship in this log plot. So here are the collision rates for different cross-sectional areas, for different target areas, because the literature shows a range of what the target area is. It could be 10 to the minus 17 centimeters squared. Or sorry, what is it? 10 to the minus 17 centimeters squared, 10 to the minus 18, and 10 to the minus 19 centimeters squared. So I tried to span the basis, span the parameter range. And then a critical line is this horizontal purple line, because that's the transition probability for the green emission at an altitude of 100 kilometers, where the green emission occurs. And so what you want really is your collision rate to be very close to this line. You certainly don't want it to be much higher because, as I said, you'll de-excite the transition. So I would say that around here, basically around here, the collisional rate is a little higher, but it's close enough to the transition probability. This line is a measurement that was taken using a spectroscope decades ago, and they measured how fast the oxygen atoms were moving, and it's around 1.4 kilometers per second or 1.2 kilometers per second. I can't remember, 1.4 kilometers per second. But if you what's the corresponding electron velocity? If the electrons, which are much less massive, have the same energy as the oxygen atoms, and you end up getting a velocity for the electrons of about 180 kilometers per second. And using that, there does seem to be a sweet spot around here that's okay. But what's right out is this other velocity, which is 20,000 kilometers per second, because it would predict much greater collision rates than could be handled, because much greater than the transition probability. And this velocity of 20,000 kilometers per second is predicted from a model which has the electrons coming from the solar wind at around 300 kilometers per second, and then they get accelerated by Alfven waves in the magnetosphere. What are Alfven waves? They're magnetohydrodynamic waves, which the electrons can literally surf and attain much higher velocities. This has been measured by satellite, but at much higher altitudes in the magnetosphere. It also has been modeled, as I said, and they've done laboratory experiments which make it suggest that it's feasible. So certainly there is an acceleration mechanism which could get the electrons going faster, and they seem to need to go faster because the transition energy requires around 1,000 kilometers per second. So here we have a discrepancy. What seems to be necessary is a velocity of about 180 kilometers per second. The actual transition energy, the energy required to get it up to its excited level, is more like 1,000 kilometers per second. And then there's this stuff going on at much higher altitudes of 20,000 kilometers per second. So yes, we explored the parameter space, but we got a little more confused as a result. The same thing can be seen here with, this is the red emission at the higher altitude of 200 kilometers per second. It has a much lower transition probability, 6.3 times 10 to the minus 3. That's this purple line way down here. Compare that with what the green transition probability was way up here. And again, we see that the lower velocities seem to be most compatible with intersecting the collision rates at reasonable rates, not too much greater than the transition probabilities. So this diagram does explain why you don't see the red emission at the lower altitudes, because the green emission would have a much greater at these lower altitudes, the red emission would not make it because the densities are much too high, right? And you'd end up getting a much higher collision rate. Okay, so I know that's a little bit of going into the woods, but this led to some conclusions, at least, that perhaps there's an auroral cascade model that might explain these issues of disparate velocities. So you can start with incoming electrons from the solar wind, and they range from 100 to 500 kilometers per second It takes about 2 days for these particles to make it from the sun to the Earth. And a good average is around 300 kilometers per second. And that's not enough to actually get the electron excited to the level that it needs to be. Then possibly there's this acceleration at the upper levels, upper magnetospheric altitudes, accelerate those electrons to 20,000 kilometers per second. There's good models and some measurements in favor of that. But then that's just too high. So perhaps the electrons then precipitate to lower altitudes and higher densities where they acquire lower velocities. For example, 1,000 kilometers per second for the excitation mechanism. And the remaining energy of the collision between the electron and the oxygen atoms might be enough to jostle them to the observed velocities of 1.4 kilometers per second. And if that's in an energy equilibrium with the electrons, then you could get your electron velocities to 200 kilometers per second. But there's a lot of gaps. There's a lot of holes in this scenario. And so more investigations are needed. First off, the spectroscopic measurements that we were able to find go back decades. Basically, you get a spectroscopic line like I showed early on, and you measure its width, and the width gets broadened as the velocities increase. It's Doppler broadening, similar to the Doppler effect with sound. It also occurs with light. And from the Doppler width, you obtain the velocities of the atomic oxygen. And as I said, the data, these measurements are old. I think they need to be redone and redone with better instrumentation that's now available. We were not able to find anything newer than what we got, decades old. So that would tell you about the oxygen atoms in the auroral zone. And then it would be very helpful to actually get velocity measurements of the atoms in situ, and the electrons as well at these auroral altitudes of 80 to 300 kilometers. But this is a tricky business. This is very difficult because you're above the balloon altitudes. You can't get up here with balloons, and you're below the satellite altitudes. And so it's a special zone where it's difficult to get a probe where you need. Probably sounding rockets are probably the best way to do it. I'm not sure, but that would be a wonderful thing to have. And then finally, get some better verification of the electron acceleration via those Alfven waves that occur at higher altitudes in the magnetosphere, and evidence for this precipitating cascade to lower altitudes and lower electron velocities. So that's what's necessary to fill in these gaps. And perhaps the biggest thing is to try to actually get in situ measurements of the atoms and the electrons. So basically that's it. That's all I have for you. If you want, I could email you the paper that this is based on. But in the meantime, I thank you for your attention, and I hope that you get to see some auroras soon yourself. Okay. So now I'm going to stop sharing. Where is that? Stop share. I just saw it. Come on. Okay.
Can I ask questions?
Yeah, now's the time.
I thought you recorded the question, the Q&A as well.
Yeah. Okay, we got the gallery. All right, we're all set. Oh, should we have speakers one at a time? Maybe the speaker. Okay. All right, Bill.
Yeah, I was just wondering, I mean, it looks like interesting work there trying to figure out what's going on, but you focused on oxygen a lot. You didn't look at nitrogen that much?
No, didn't try it. I basically stuck with the dominant mechanism of oxygen. It was, I figured atomic line emission is easier to understand than molecular band emission.
Right, there's no atomic nitrogen up there?
Apparently not. There's both molecular nitrogen and charged molecular nitrogen, an ion, a positive ion of it. So that would be something to work on as well. It's rarer, the nitrogen emission.
Right. Okay.
But I could challenge you, Bill.
In what way?
To do similar work on the nitrogen molecule.
Okay.
There was some things in the chat I want to just, while waiting for other people to chime in. Stunning images. Bill, you said that the island that I said was Ellesmere Island was actually Baffin Island. So that's true. Dancing curtains. They remind me of, what's that candy? Ribbon candy? That candy that is impossible to eat because it digs into your gums. And here you have, you're guessing that the Zooniverse projects help to train artificial intelligences that will take over eventually. Yes, a lot of the Zooniverse projects, I don't know about the Aurora Zoo, but a lot of them are providing ground truths for AI, for artificial intelligence.
Yeah.
And you're thinking that there's a collision between the high energy electrons and those of the atoms and molecules of the atmosphere.
Yeah, well, you were just talking about, when you're explaining the mechanism for the excitation of those spectral lines, there are basically two colliders. Well, the two sets of colliders, one of the atoms and molecules, which
Right.
can give you sort of a thermal equilibrium of distributions. And then there are high energy electrons coming in, which give you these high energy lines, these higher energy lines.
Yeah.
Yeah.
So, okay, good. All right. Any other folks want to chime in? Anybody have any tales of auroras?
When I traveled to Asia, I had a chance to see auroras from the airplane for hours, and it was almost hypnotic. Going over Alaska, coming down over the Kamchatka Peninsula to Japan or Taiwan or Korea. It was just a beautiful display every time the flight took that route. I thought the sun having CMEs with material, now that was coming from a plasma, and it's not electrons, that would be ions, wouldn't it? I mean, ions of material, and that interacts with the Earth's field and creates electron discharges that come into the atmosphere to interact with the gas at different altitudes. Is that what you got it put together like that?
Well, that's what I thought mostly, that it wasn't the same particles that were colliding with the atoms in the atmosphere. That you initially have this plasma from the sun. Yes, it's both ions and free electrons, and most of the ions are protons. Maybe
I thought the plasma from the sun would be a hydrogen helium.
That's it.
Plasma.
Right. So you have the hydrogen nuclei, which is the proton, and then the helium nuclei, which is which is two protons and two neutrons. They're coming at us, but also the electrons, so that the net charge of the entire plasma is zero. And apparently these are the same electrons which somehow make it down to lower altitude. So I was kind of surprised. I thought it was a pinging of the magnetic field, and then the disturbed magnetic field would induce currents of material that's trapped in the magnetosphere. So
It's like snapping rubber bands, where the magnetic reconnection sort of snaps and comes back down, right?
right. And there is in the literature the phrase secondary electrons. And so that's subject of further investigation. We were not able to get to the bottom of it. And, I wish I could get a real auroral research here to set us straight.
It's great to listen to all of this. Thank you.
It's a neat mystery. It's a very magical little zone that we occupy, and the currents are powerful. Apparently they're enough to power a city like Toronto.
You gotta harness it.
Yeah. Anybody else have any aurora stories?
Mostly from
I do
my,
have one.
Yeah.
Sorry. And sorry I was late. I was working on something.
It happens.
With NSAC, we went up to, we used to call them the Frozen Toes Star Party up in Maine, this field in Maine. And I had my 18 there, and they had the 36-inch F5 Dobsonian there, Godzilla, and some very expensive refractors. And it was a beautiful night. And we had all this equipment out in the field. And all of a sudden, our darkness went away. We thought, what is that? We drove all this way. We thought those lights coming on in the next town over or something. And then it turned to the red and green sheets and the going across the sky. And the memory that I take with me from that, and the point of this whole exercise, is just the sight of all those people wandering around, $150,000 worth of expensive astronomy equipment lying fallow.
Right.
While all these astronomers walked around gazing up, practically drooling, going, ooh, ooh. So that's my story.
Do you remember the date?
No, I don't. I know it was really cold.
Maybe that's why you don't remember the date.
Oh, that could be.
Dan? Dan?
yeah, I saw several up in Iceland 4 years ago when I was up there.
Oh,
I mean, you just walk outside and there it is.
even in the city?
Yeah, even in the city. Well, the city's not that bright.
Oh, good.
There are lights, but it's not that bright.
And were you able to see any color?
Just green.
Screen. So cool.
And also on the plane there and back, you can see
Oh.
it for quite a while.
Oh, I wanted to ask both you and the other fellow, was the aurora as seen from the plane above you or below you? It must have been above you still, right?
Yes.
Yeah, the plane doesn't get up that high.
Yeah. Okay. All right. At least that makes sense. It must be wonderful observing the aurora from the space station. That must just be
Oh.
incredible.
Now you're looking down on it at that point.
Yeah.
I wonder about the top of those cloud formations where you have the discharge, that the sprites and the other discharges that go up from the cloud lightning strikes, sprites and something else. And they only see that from the space station.
Yeah.
It's an interesting field.
Yeah, we almost, I think he wanted to, initially, Wu Cheng Ma wanted to consider all these discharge phenomena, but we ended up just trying to focus on one, the auroras. But the sprites activate, I think, the same emission. And then there are these things called steves. And I don't remember what the acronym is, but those are these long linear glowing phenomena which can be confused with contrails unless you look carefully. And so strong thermal emission velocity enhancement. Thank you, Bill. And those seem to be getting noticed more and more. Maybe it's because of our climate is changing, who knows? So, anybody else? Okay, because otherwise, that's all I got.
That was well done. Thank you.
Thank you very much.
Yeah,
Okay,
thanks, Bill.
I'm green. I'm for me, I'm green with envy, let's say.
green with envy. Oh, that's so bad, Buzz.
Now Bill's saying red.
Thank you, guys and gals.
Thank you very much. Thank you.
All right. Take care, everybody.
Good night.
Bye-bye.
Bye.
Green with envy.